In this video, we'll be diving into the process of how we implement and fit a structural equation model. Now, I say the process according to me because there are a variety of perspectives on what the correct process is. I think the process we're going to talk about is one that's generally approved. It's pretty close to something called a two-stage process, but it's the one that I use and makes sense to me. So for step one, we'll be identifying the model and measurements. And as part of this, you're going to have to know your research question really well and some other things that we'll discuss. I'll say some people break this into step one's know your research question, and step two is identify the model. But these are necessary things to kind of prepare and get ready for exactly what you're going to end up testing. Step two is performing a confirmatory factor analysis to evaluate what's called the measurement component of the model. And if you think of this structural equation modeling as a combination between confirmatory factor analysis and path analysis is where you're drawing all the relationships between the variables and latent variables. Confirmatory factor analysis is where you're drawing all the relationships between the items and their factors, and we call that the measurement model. So here in step two, we're really seeking to evaluate the measurement model and trying as much as possible to ignore the path analysis component. In step three, then we include the path analysis component and estimate the whole structural equation model and assess the model fit. Just like in CFA, we tend to have multiple models. So this is also where we compare multiple models together. And sometimes if I'm just looking to see what theory fits best, this step three is where I make that decision. Step four, if I'm looking at assessing particular relationships as my research question, is that after everything looks good and I'm confident that my model is the correct explanation for the underlying theory, I can go on and assess the relationships between the paths. So, step four is actually interpreting those paths, and we'll have statistical significance tests and other things that we can use. These steps are pretty close to the two-phase approach, but again, there's lots. There's a one-phase approach, there's a two-phase approach, there's a four-phase approach. There's a lot of different phases, a lot of different steps that you can do. So these are what I tend to do when I'm running a structural equation model. Step one, identifying the model and the measurements. So again, to start, you really have to have your research question extremely clearly articulated. You have to know exactly what you're talking about and exactly what relationships you're identifying in order to implement a structural equation model. In some other models, you can be, or some other analytic approaches, you can be a little more fuzzy, and certainly in unsupervised methods like exploratory factor analysis or cluster analysis, you don't really have to know. You just toss it in the computer and it'll spit out some stuff. But in structural equation modeling and confirmatory factor analysis specifically, you have to be able to articulate very explicitly what you want. Additionally, in a structural equation model, you need very, very clear measurements. That is, you need to know exactly how each of the factors in your research questions are going to be measured, exactly how many items there are going to be, exactly where the items are going to load, and exactly how many factors. So you need to be extraordinarily clear on all of these things before you can implement your structural equation model. And frankly, after you've done these first two bullet points, the drawing part is pretty easy. So sometimes people think of this first point as the drawing, and it is in many ways. But the thing is that you have to have a ton of information to be able to make that drawing. In fact, I like to say that for these first couple bullet points, while you're trying to articulate this, you may already draw it out to try to help you articulate this because of how explicit you really have to be with identifying your research questions and identifying your measurement model. So all of that needs to be extremely clearly articulated and then drawn out so that you can specify explicitly all of the things for your research question and measurement model. Now in CFA, we drew covariances between all pairs of latent variables, and that's how we approach our confirmatory factor analysis. But in the structural equation model, we're going to use directional arrows to specify where we think the relationships are. So we'll use directional arrows to say, I think variable A impacts variable B, and that'll ultimately treat variable A as our independent variable B as the dependent variable, or using the structural equation modeling language, variable A is the exogenous variable B as the endogenous variable. Now, structural equation modeling, just like CFA, is often used to compare competing theories. So, in addition to performing your identification and model for your theory, you should also figure out what other competing theories are around that explain the nature of the relationships between the variables that you're studying. So, in considering these possible alternative relationships, it's kind of expected that you do things that I mean, do any that kind of agree with you, but also do things you may heavily disagree with. If it's a explanation or a possible explanation in the theory or the literature, even if it's one you disagree with, but it's an explanation for the relationship between the variables you're studying, it's worth dropping that in there, and it's really expected that you drop that in there. Um, as something you're going to assess. At the end of this process, you might have a couple or a series of different models that you're testing, all of which have different explanations of the underlying theoretical relationships between the variables you're interested in and assessing. And ideally, your explanation of the interrelationship between these variables is going to be the best one. So it's great to have all these different models. It's important and necessary to have all these different models so that you can articulate and quantify the degree to which your theory compares with other theories numerically. If you don't have common relationships between the models that maybe is a common theory in your field, it might look questionable to say, hey, you've proposed this new way of looking at relationships among variables, but you've not compared this to the old way of looking at relationships among variables, and that's a big miss. So we want to see that relationship and that comparison happen so that we can determine, hey, is yours better than that alternative? Almost making comparative model fit as important as that objective model fit. So we do want to have these other hypotheses, especially if they're common in the field. Um, and we want to compare to all of these reasonable possible theories. Don't just pull the ones you want. Don't just pull the ones that you think are bad. Pull the ones that you think are good. And again, compare yours to every reasonable theory about the relationship between the variables you're studying, if you can. Now, I want to qualify this a little bit because while we do compare to other theories, what I'm not saying is that we should collect additional measurements to test other theories. So the theories that we should compare to are theories that explain the relationships between the variables that we are studying, not necessarily other variables. So don't, if there's another theory that says, well, here's 10 other variables I think are related, you could go gather them if you're doing it in initial data collection. But if that's not something you're studying, or if you have to really completely change your study in order to compare to a particular theory, that's not what I'm talking about. What I'm talking about is that if we are looking at, say, 5 different variables, and your theory has a particular arrangement of those 5, but so and so in the literature has a different arrangement of those 5, you would run both of those models through this process. And then at the end, you could compare directly the models to each other using AIC or the chi-squared if they were nested, and say, I think this one works better than that one, or this one aligns better with the data than the other. And you could use that to then guide which theory seems best supported by data. All right, step 2. So for step 2, you simply do the confirmatory factor analysis. All the steps that we indicated before for CFA, you do for step 2. The goal is to assess the measurement of the latent variables and not assess the appropriateness of the path specifications that you're going to make in your CFA. So because of this, what you're going to end up doing is still have the covariances between all pairs of latent variables in the CFA. So you're not specifying paths at this stage. You're doing covariances between all latent variables. And the reason for that is, again, the goal of the CFA is to assess the measurement component only, not to assess the appropriateness of the paths. That'll come in a future step. So we have covariances between all pairs of latent variables, as is typical in the CFA, and we run that confirmatory factor analysis. Now, if this confirmatory factor analysis is bad, you can try to fix it, subject to the typical CFA constraints. We talked a lot about how it has to be theory-based, talked a lot about suggestions, talked a lot about how if it is, if you go too far, then really you're no longer doing confirmatory factor analysis, really you're engaging in exploratory research. So subject to all those constraints, you can try to make a model improvement and fix the measurement model. But if you can't fix it, you may need to stop. And this is hard. This is really hard. It's happened to me. It's happened to many researchers that ultimately you have a measurement model that's just intractable. I just can't. I just can't fix it. It's just too bad. And you ask, hey, can I move beyond step 2 in that particular case? And it kind of depends on who you ask, but consider why maybe that's a bad idea. Why do you need to stop if you can't get beyond that? If you can't fix the measurement model. And consider this, if I'm looking at the relationship between several variables, but I'm not confident I'm actually even measuring those variables, how can I really assess the relationship? That is, if I have a measure of intelligence, but I'm not really, the measurement model doesn't seem like it seems to be working for the intelligence variable, then any conclusion I make on quote unquote intelligence, well, I'm not even sure that I'm measuring intelligence. So I'm not sure I can actually make any conclusions in the first place. So if you're not confident in what you're measuring, I'm not sure how you can discuss relationships between things that you quote unquote measured because you don't even know what you're measuring. So that's the argument as to why if you can't fix the measurement model, this is really a hard stop on the research potentially. Now I do think there are some exceptions here, but this is a hard stop. Now, one thing you could do is move to a path analysis. So remove the measurement model, just take the averages for each of the variables. But it's worth mentioning that this simply ignores the problem. All you're doing is hiding the fact that you have a bad measurement model behind taking averages for each of the variables. So you're just hiding that away. And again, depending on the context, maybe that's semi-appropriate, but it is important to realize that while this could move you forward, it doesn't actually fix the problem with the fact that it seems like maybe you're not measuring what you think you say you are. On the positive side, if this looks good, if the measurement models looks good, then what you're saying is that when we're not accounting for the paths, when we're just looking at the measurement, things are great. So if things break later on when we assess the paths or when we add in the paths, we can tell that it's not because of the measurement, it's just because of the paths. So we like a good measurement model because it serves as our foundation. And then we add on the paths and we can see, are these paths fitting well with what's being described by the data? If so, we'll still have good model fit after we add those paths in or specify those paths. And if when we add in the paths, all the fit statistics then turn out really poorly, then we can feel confident, okay, the only thing that changed was the paths. We already did the measurement stuff when we weren't worrying about the paths. That looked good. So if we add the paths in, it must be the paths that are the problem. And again, that's what we really want to study in SEM. I'm trying to take into account this measurement stuff, but what I really want to study is the relationship between the variables. So it's nice to have a nice firm measurement foundation such that I can make better conclusions about the relationships between the variables. All right, so step 3 is actually estimating the model and assessing fit. So the model estimation, usually maximum likelihood, and measures fit are all identical to what we did in confirmatory factor analysis. Again, we have multiple competing models, and if we do, we should calculate these fit statistics for all of the competing models. And we, similar to confirmatory factor analysis, have a couple of different options here. We have the overall fit, just looking at general, does the model fit well? We have our rules of thumb and stuff. Poor overall model fit. If we had that strong CFA foundation, and then so all of our model fit statistics look good at the CFA level, and we added in the paths, and now all our model statistics, fit statistics look terrible. That indicates that the paths are what's the problem. The paths are not doing a good job at capturing the relationship between our variables, latent variables or otherwise. For comparative fit, again, we're comparing our model to other possible theories, and this would tell us if our model is doing a good job or a bad job in comparison with other theories. Poor comparative fit indicates that other models are doing a better job at explaining what seems to be going on. That is, the data align better with the relationships reflected by other models, and the data don't line up as well with the relationships reflected in your model. So maybe the other models and the relationship that they express are closer to what's actually happening than what's expressed in yours if you have this poor comparative fit. So we can do this. We look at all of our models. We look at the overall fit. We look at the comparative fit if we have multiple models and see. And again, coupled with a strong CFA, this can indicate where the problems lie. That is the problem a path issue, or if the problem's a measurement issue, we'd have addressed it in the previous step. And frankly, that's the whole point of the two-step model. To make it a one-step model, you just take out the CFA evaluation. You jump straight from step 1 to step 3, and don't look at the measurement model. That's the one-stage approach or the one-step approach. All right, so again, if you were just looking at comparing multiple theories, maybe the previous slide does it for you, but if you're actually looking at the nature of the underlying relationships, step 4 is interpreting those paths. So after you are confident in your model, it's a good fitting model, it fits better than the other theories, the measurement's good, the paths are good, then you can look at examining what the paths are. So are they positive? Are they negative? Are they statistically significant? Are they not significant, et cetera? And you can establish those relationships just like you would among normal regression in the sense of, do my independent variables affect the dependent variables? Of course, you can get much more complicated in the SEM path analysis framework, but you can also stay basic in the regression world too. There are statistical significance tests that are available for the paths, so you can use those to determine if the relationships are statistically significant. And while you can use unstandardized paths, standardized paths are typically more meaningful to provide and interpret. Though I say this, both are typically provided. So typically what happens is you'll see an unstandardized path with the stars for the significance level, and then you'll see the standardized path in parentheses afterwards, indicating, hey, this is the standardized path. So you'll see both. You'll see unstandardized path, stars for significance, and then again, parentheses standardized path, which typically is what's interpreted. And it's worth noting, standardized paths are analogous to standardized regression coefficients. So that's in our review section. I think it might have been for the confirmatory factor analysis, but that's why we talked about it, because these standardized paths are the same as our standardized regression coefficients. All right, well, this has been a discussion on the steps, the protocol for implementing a structural equation model. Next, we'll go through a quick example of how this could be done, and then eventually jump into software.